Hi, today we're going to continue on our thread before of looking at acid-base titrations, but we're going to add another layer, which should make things, just a touch more complicated, but hopefully drawing on what you saw before, this shouldn't be too weird. Similar to what we did last time, we'll try and run through the AP example, and then I'll try and streamline things a little bit for you. So just to get your mind in the right zone, to bring you back to where we were before from the last lesson. Just the biggest difference between a hydrochloric acid solution and an acetic acid solution. Take a second. Okay. So clearly one of these, this is a strong acid, this is a weak acid. Here, the H plus concentration is going to be equal to 0.1 molar. Here, the H plus concentration is going to be something less than 0.1 molar. And this tiny fact, this tiny difference will be the guiding principle, the driving force behind a lot of these calculations being different than what we saw before, because there's this added step of equilibrium has to establish instead of just taking it at face value. This should make things, like I said, a little bit more complicated, but not terrible. So instead of titrating a strong acid with a strong base, we're going to titrate a weak acid with a strong base. And I think the biggest difference we're going to see is right here. With a strong acid solution, your pH would usually be something down here before it shoots up. And now we're going to see this big difference. So we still have our same regions. This would be region 1, this would be region 2, this would be region 3. Keep in mind this would be region 0, right? I labeled that last time. So largest difference here. Although what I will say is it does seem to be that the equivalence point pH is not 7, so there's also going to be a region 2 consideration. I can't really comment as to region 3's difference, so we're going to leave it for later. But today we're going to take a look at, like I said, acetic acid. So when we mentioned before, we looked at hydrochloric acid or hydrobromic acid before that, but more or less the same thing. Just for the sake of argument, we're going to ignore activities just for this whole thing, just to make everyone's life a little bit easier. Here we have our Ka value for our acetic acid, 1.756 times 10 to the negative fifth. We've got a 0.02 molar acetic acid solution, a 0.1 molar sodium hydroxide solution. So given that information, we could probably figure out the equivalence volume, which should be equal to, we're looking for volume of base, right? So remembering our old titration equation. VB here, we're going to call VE. So in other words, VE is equal to MAVA over MB, or 0.02 molar times 50 milliliters divided by 0.1 molar, which should give us 10 milliliters. This should be relatively easy also to reason out in your head. Keep in mind that we're allowed to make these general qualitative assessments here, in that if the base is 5 times as concentrated, then the volume will be 5 times smaller, so 50 to 10. That should make sense. So let's just dive right in. Here's the, I'll copy over the information for each rung, each region we're looking at. If you want to hit the pause button and try and work through this before I say something, that would be a wonderful idea. I'd say work with your neighbor. This would be an excellent lesson for me to just hit the power button on the presentation and let you all work through it. But your neighbor's not next to you, and your neighbor shouldn't be next to you, and if they are next to you, they should be at least 6 feet away, because that's what we're doing right now, but I'm getting ahead of myself. I want you to hit the pause button and try and figure this one out. The best question I think you can think of for this whole process is, what does what do the contents of the beaker look like? What's in the beaker? Because that's really going to guide the math behind what you're looking at. So I'll stop talking. Take a couple seconds, make a plan. So if you actually draw out what's in the beaker, what we're starting with is we have all HA, and we haven't added any base yet. So what we have here is your solution, and you've got mostly some HA. The solution is laughing at me. And then we also know that since this is a weak acid, a small amount of H plus and A minus have dissociated. So right now the chemistry behind what's going on in our solution is, well, this is our stereotypical weak acid solution. And for our stereotypical weak acid solution, we can write our equilibrium expression, apply our systematic treatment of equilibrium, and jump straight to our shortcut of Ka equals x squared over f minus x, where x is equal to H plus, which in this case, oh geez, I didn't solve for it. Well, I think I can solve this easily enough, right? Shouldn't take too long. Got a couple buttons to press. This is 4.756 times 10 to the negative fifth, and this is it's 0.02. And so graph. I should solve these. Well, it's just going to eat up time if I actually solve them on the fly. I should solve them beforehand. It speeds up the lesson for you guys. There we go. So our x value, our H plus value is 9.52 times 10 to the negative fourth molar, which that then would give us a pH value of 3.23. Just let me make sure. No. This makes me worried for my answer key. Should be 3.02. Huh. I'll fix that. If I'm wrong again, I'll go back and fix it. But I think I typed this all right. I think. Let me calculate the intersect one more time just to make sure. This is why I solved it all beforehand. 9.52 times 10 to the negative fourth. Yeah, that's right. 4.7. Ah! There we go. I see what I did. I typed in the wrong number. Rookie mistakes here. I'd edit it out, but you know what? I don't actually have a viable program that works with my computer, so I'm not going to worry about that. You don't need to suggest one. It's cool. Ah, there we go. I'm back on board. So this is in fact 5.85 times 10 to the minus fourth, and there we go, 3.23. I had it right. I knew the answer, I just had to make my math fit. So this is our starting point, right? No base added, all acid. Now if we just took the negative log of 0.02, like I said, we get a number larger or smaller than that, because that would be assuming full dissociation, which this doesn't have. So as we move on into region 1, like I said, we're going to approach this the same way that we approached it back in AP Chemistry, and then we're going to go from there. So 50 mils of 0.02 molar acetic acid, we're going to add 3 milliliters. Remember that the equivalence volume is 10 milliliters. This is going to be important pretty soon. So the reaction taking place is that HA is going to react with hydroxide, and that will be a one-way reaction to create A minus and water. The key component here is that if V is less than VE, hydroxide is limiting. So in your end solution, what we're going to end up with is, instead of mostly HA with a tiny amount of A minus, with our products, we're going to get a reasonable amount of A minus and a reasonable amount of HA. This is a buffer. Anytime we have an appreciable amount of acid and conjugate base. So as we're dripping in the strong base, in this case, the solution that we have in the middle, in between the starting point and our equivalence point, is a buffer, which really opens the door to a lot of quick math. So whenever we're approaching a buffer situation, obviously we want to set up an ICF table. So I'm going to fill in the moles really quick. Our initial amount of moles here of HA is 0.001 mole. Our initial amount of hydroxide, 3 mils, 0.1 molar, so that's 0.0003. And our original amount of A minus is nothing, so again it's limiting, so minus 0.0003. And then we're going to get, obviously, 0.0003, 0.0007. At this point, we would divide by the total volume and then use that, but, you know, we can be a little bit better than AP here just to save some time. The pH here is going to be equal to pKa plus log of base over acid. In this case, that's going to be equal to 4.756 pK of acetic acid plus log of 0.0003 over 0.0007. And that should give us a pH value of 4.38, which I like. And then hypothetically, you can go through and you can do that for each pH value. But in order to speed things up a little bit, now I've got the same setup here with a slightly different number. We're now at 5. And this is going to do me, I'm going to go through this a quicker way, and this is going to do me the favor of showing two things at once. So first, if we were to go through the ICF, we'd have the same 0.00, what was it, 1. And then this 5 here tells me it'd be 0.0005. Which becomes the same number of A minus, and then this would become 0.0005. Now, since this is a buffer, and since dilution doesn't matter and the volume doesn't matter because it's one container, I think like the best thing to focus on is just the relative ratio of base and acid. And the relative ratio of base and acid can actually be related back to the equivalence volume. So instead of saying I've added 5 milliliters and then doing all the mole calculation, you can say 5 of the total, 5 of the 10 total have been added. So you're 50% done with titration. A different way to say that is you have 5 parts acid and 5 parts base at this point. So in plugging in, you should still say pH equals pKa plus log base over acid. But instead of putting in all these decimals, you could just say 5 over 5. Now this is going to show you two things. First, we know that in a buffered system where you have equal amounts of acid and base, pH equals pKa. So this tells you something about a weak acid titration. At the halfway point, when V equals 1/2 of the VE, pH equals pKa, as you saw down here. But secondly, this represents a nice little shortcut that we can use moving forward. In fact, you kind of could see it if you look back here. The ratio is still 3:7. I mean, there's all those decimals there, but when you have 3 milliliters added and VE equals 10, you've got 3 parts base and 7 parts acid. And you can kind of use this ratio in terms of the equivalence volume and the amount that's currently present to really speed up the calculation of each step of the way, just setting up that ratio instead of going to moles or molarity. And we're really peeling back the steps here. So once you reach the equivalence volume, this doesn't have a special way of looking at it. You just need to kind of think about the problem. We have our chemical reaction. The extra consideration here is that the moles of HA equals the moles of hydroxide. So there is no excess, there is no limiting. It's a 100% A minus solution. But when you have a solution of A minus, you have to remember that A minus is in fact a weak base. And so there's going to be a small amount of HA created and a small amount of hydroxide. And so really, while this is the reaction that happens in the titration, once you hit that perfect equivalence point, what actually takes place is that in that solution, a tiny amount of the A minus will back react to recreate a small amount of HA and hydroxide, and it's this reaction that's going to guide the pH of your solution. The pH of that solution, though, this reaction is governed by Kb. So in this case, we actually need to use Kb equals HA times hydroxide over A minus. Now there's a very, very big change, because I know what you want to do. You want to just say x squared over 0.02 minus x, but there's a very big change that's happened to this solution. We've added 10 milliliters of base to this 50 milliliters of acetic acid to make our solution of acetate. That means we now have 60 milliliters of stuff, so we can't do this. This doesn't work. Now, in a buffer, we said that dilution doesn't impact your overall pH because it's a ratio of the concentrations. We're not in a buffer anymore. You always have to consider, if it's not a buffer, any dilution effects that took place. So really what I want to write here is that Kb is equal to x squared over f prime minus x, where f prime is your diluted formol concentration. In this case, it's going to be equal to F times the initial volume over the new total volume. In this case, 0.0200 molar times, we start out with 50 over 50 plus 10, and that's going to give us 0.0167 molar. So when we plug that in, x squared over f prime minus x, and using Kb, we should get 5.702 times 10 to the negative 10th Kb equals x squared over 0.0167 minus x. And then this will give us an x, which is a hydroxide, of 3.086 times 10 to the negative, I keep writing 10th, and I don't know why, 6th molar, and pH, you know what, I'm going to write that up here. pH equals 8.489. This number should make sense because if we're titrating a weak acid with a strong base, the equivalence pH is greater than 7. Weak acid, strong base, it drives it basic. That's how I remember it. And so finally, can I clear all this? Uh-oh. I'm going to go crazy with my eraser. I can't? What? Oh. I don't know what just happened. Cool. I'm moving on. We're going to consider region 3 again. We're in excess, so we set the process up the same way. I need one more zero. I need my eraser now. Getting frazzled. 0.00, yeah, 100 moles. That's the same acetic acid that we started with, except now that we've added 10.1 milliliters, we have 0.067 0, 1, 0, 1 moles of hydroxide and 0. So what we're going to do is we're actually going to consume the HA. The HA becomes limiting. So we have in our solution we actually have in our solution a bunch of A minus. And now you want to say that like A minus is a weak base and you create a little bit of HA, except we have extra hydroxide. So that's actually going to stress that KB reaction even further to the point where there's essentially no HA. And I mean, honestly, even if there was any HA, the amount of HA that you create and then the corresponding amount of hydroxide you create by doing that is so negligible compared to even this tiny amount that this is going to govern the pH. There's still some hydroxides floating around in solution of the excess sodium hydroxide that you added. So this is what we're going to look at. Now this, don't forget, is a moles table, so we have to actually take that and figure out our hydroxide by saying 0.00001 moles, and then we have 0.0601 liters, and then that should give us 1.66 times 10 to the negative fourth molar, and that would then yield a pH value of 10.22. So, and then you just go through this process and figure out your moles and figure out your moles and subtract and get your excess, and then you get your answer. And that works well. But we don't need these ICF tables if we're smart about it. Because really what happens is if you're aware that you're just targeting the hydroxide, I mean, basically you can kind of just consider the amount of hydroxide that isn't consumed by the reaction. In other words, this 50 milliliters of acetic acid will make this first 10 milliliters of hydroxide like not exist. It turns it into A minus. So really, the current amount of hydroxide you have is equal to the initial amount, but then it also is diluted. So in other words, kind of how I'm looking at this is I'm adding 0.1 milliliters of base to 60 milliliters of stuff, because that first 10 at this point is basically water, right? We know that HA plus OH minus will yield A minus plus water. In terms of hydroxide, the first 10 milliliters of base isn't even hydroxide anymore. It's gone. So we've got the excess over the total, in this case, is going to be 0.100 molar times 0.1 over 60.1. And that's going to actually, if you go through and check the math, we're going to get the same 1.66 times 10 to the negative fourth, and your pH will still be 10.22. So again, go through this, like watch through the steps. I tried to keep the regions the same. Region 1 is before the equivalence point, region 2 is at the equivalence point, region 3 is after. There is still the region 0, but the key component here is to sit back and think about what chemistry took place and what that does for the components of your solution, and then to execute the right appropriate math to line up with the chemistry that you know took place. Thanks for watching.